With the BS code, if you provide T12 at 125, the slab will pass in deflection. But based on the Eurocode, if we use T12 at 125, the slab will never pass because the difference between these two is too wide. So the only thing you can do is to increase the thickness for the Eurocode, but for the BS code you can adjust the reinforcement provided. Welcome, this is Chevdin Academy. In this video we want to compare the slab design approach in Eurocode 2 to that of BS 8110. I'm sure we're all familiar with the two codes, the Eurocode and the BS code. I've created about 2 videos on this topic where I compared a lot of things about the Eurocode and the BS code. You can check out this video now to watch that, or you check the description of this video. So for the purpose of this video, we are going to be making use of this layout. This is a typical floor layout that has 8 panels, in which 2 panels are similar. So in order for us to deliver this practice example, so you only need to design the critical slab, the critical panel out of this. And we know that the more the discontinuity of a slab, the more critical the slab. So we can say that from this approach, we can see panel 1 and panel 4 are the most critical panel, because it is only these 2 panels that are discontinuous in 2 adjacent edges. So we only need to design panel 1. So the result for panel 1 can be applicable to the remaining panel. This is the approach of manual design. So the first thing we are going to do is we are going to be looking at the structural loadings and combinations. And in order to do this, we compare the BS code and the Eurocode. So we have the BS code on the left hand side, the Eurocode on the right hand side. So for this exercise, we are only going to be looking at the dead load and the live load. We will not look at other dynamic loads. Only static loads will be considered. So for the dead load, according to the BS code, we all know what the dead load is about. The dead load is the self weight of the material, or the weight of permanent structure on the slab, since this is a slab that we are designing. So the dead load will include the self weight of the slab. So based on the previous slide, the slab thickness is 150, the density of concrete is 24, because this is a reinforced concrete design. So because of that, we can calculate the self weight of the slab to be 3.6 kilonewton meter squared. Then other dead loads include finishes, partitions, and service load. So finishes, we can assume a concrete finish of 75 mm thick. So we multiply by density of 22 to give 1.65. For partition load, we can assume 2.5 kilonewton per meter square, depending on the type of slab. Then we also have service load, which include all other loads or appliances that can be attached to the slab. Service load in terms of ceiling fans, electric bulbs, and every other appliances that might be attached. So we assume a service load of 0.5 kilonewton per meter square. So therefore the total dead load is 8.25 kilonewton per meter square. But if you want to consider the Eurocode, dead load for the Eurocode is quite similar. For those that are familiar with the 2 codes, you know that the 2 codes are based on the ultimate limit state, the limit state design. They are both based on the limit state design. So it's more or less similar in terms of the loads. Here we're also going to consider the self weight of the slab, but the only thing you notice here is that the density of concrete here is 25. This is because the Eurocode tends to increase the density of reinforced concrete by 1. So instead of 24 here is now 25. So this increased the self weight to 3.75 kilonewton per meter square. Other things remain the same: finishes, partition, and service load. So according to the Eurocode, based on the Eurocode, you can have a total dead load of 8.4 kilonewton per meter square. So now to the life load. The life load is based on occupancy, the purpose of use of the slab. So let's assume a banking hall for this slab. So let's assume a life load of 3 kilonewton per meter square, and we assume the same thing for the Eurocode because we want to compare the designs and see which one is more economical and which one is more reliable to use. So we have combinations because you have to combine the dead load and life load. So therefore our design load, if you are using the BS code, we all know that when you have dead load and life load as the only contributing load, we apply an ultimate load of 1.4 times the dead load plus 1.6 times the life load. So substituting for dead and life, so you end up with a design load of 16.35 kilonewton per meter square. Then to the Eurocode, the combination is a little bit different. So instead of 1.4 for the dead load, the Eurocode provides 1.35 for the dead load, and instead of 1.6, the Eurocode provides 1.5 for the life load. So at the end of the day, even though the dead load is slightly more because of the increase in the density of reinforced concrete, so because of that the dead load increased, but based on the factor that we have to apply for the combination, the design load is slightly smaller compared to the BS code. So the design load for the Eurocode is 15.84 kilonewton per meter squared. So this is structural loadings and combination based on the BS code and Eurocode for slab. So before we continue, if you are interested in learning more about design, especially manual design to either the BS code or Eurocode, you can visit our website chefginacademy.com. We have a full course where we explain how to design manually. This is our website. This is the course. This is manual design to the Eurocode. So this course is huge. We have about 20 hours videos. So the materials include 84 hours video course. You have access to the Eurocode text, all the Eurocode text. You have access to how to design to the Eurocode manual design, and this course is project oriented. So our course are project oriented. So what we do is we start design from the conceptual phase to the delivery phase. So all the stages involved in design, we look at it from the beginning to the end in this course. And then you also have access to calculation templates. So based on the Eurocode, we've already designed a calculation sheet that will guide you in your practice. So if you take this course, not only that you will be having access to video guide on how to design and also practicing using a real life project, you also have access to calculation sheet template, which is free. You don't need any design knowledge. Once you have at a novice level in AutoCAD, then you are good to take the course. So this course, the course project for this course is a public building, a G+2 public building. That is what we use for this course. So and then if you want to take the design to the BS code, you can refer to this course. This course is for the BS code, while this is to the Eurocode. So let's continue with our discussion. The next thing after design is analysis. So if you are familiar with the BS code, if you want to analyze slab, the BS code recommends moment coefficient, especially when your slab are fully restrained by beams. So when they are restrained by beams, the moment coefficient method is what we usually use to analyze the slab. If you look at the Eurocode, you will see that the Eurocode did not really talk about slab analysis. But if you check design manuals to the Eurocode that tries to explain the Eurocode, you see all the provision that we have in BS code for slab analysis was also what we can find in the Eurocode for slab analysis. So therefore, the analysis method proposed by the two codes is the same, using the same moment coefficient factor. So because of that, 2 moments at the midspan of the slab and also 2 moments at the continuum. So we just want to pick the maximum out of the 4 for this exercise so that this video will not be too long. So for the BS code, if you use our design load of 16.35, your maximum bending moment is 22.89. For the Eurocode, if you use 15.84, the design moment is 22.18. You can see that the moment is quite similar and very close. So, and then for us to design, we need to calculate what we call the effective depth. Either you are designing using the Eurocode or BS code, is the same thing. So the effective depth is the height, thickness of your slab minus the cover. We are assuming a cover of 20 mm minus half diameter of bar. So we assume a reinforcement size of 12 mm. So at the end of the day, we have effective depth of 124 for both Eurocode and the BS code. So now that we've analyzed the slab, I don't want to go through the whole process of the analysis. It's very long. I just tried to shorten it and bring out the result in this video. So if you want to see a full video on how to do that, you can check out the 2 courses that I've recommended, either to the BS code or to the Eurocode. So the next thing is to design. So we are going to be looking at the bending reinforcement. In slab design, we understand that we try as much as possible not to apply concentrated load on the slab. So when you avoid application of concentrated load on the slab, you don't need to check for shear reinforcement. The only thing you need to check for is the bending reinforcement. So bending reinforcement, according to the BS code, is quite straightforward. So we know this formula, m over bd square over fcu. So this formula is used to calculate k. Our k, so if you substituting moment of 22.89 for the BS code, in slab design we take the width of slab of 1 meter. So that's why b here is 1000 mm, d is 124. Then we assume fcu is the characteristic strength of concrete. It is usually determined from the design mix you want to use. So we assume 20 Newton per millimeter squared for this design. So once you compute that, your k equals 0.074, and this k value according to the BS code must be always less than 0.156 if the section is going to require only tension reinforcement, which is applicable here because this value is less than 0.156. So because of that, our section requires only tension reinforcement. We can now calculate the lever arm. So I don't want to bore us with the formula of calculating lever arm, so I just put it here. So if you want to see all that, you can check the Eurocode or you can take the course that I recommend for you earlier in this video. Then here we can calculate the area of reinforcement once we know our Z. So the formula according to the BS code is m over 0.95 zfy. M is the design moment, Z is the lever arm that we calculate, Fy is the strength of reinforcement you want to use. So most of the time we have 2 major types of reinforcement. We have the mine steel and we have the IE steel. So the mine steel have a strength of about 250 Newton per millimeter squared. The IE have a strength of about 400 to 500. So the most common one in my own region is Fy of 410. So if we substitute moment 22.89, Z of 112.8, Fy of 410, then we can see that based on this our section, the reinforcement area, the area of reinforcement required is 521 millimeter squared. So we can just provide T12 at 200 because in slab the reinforcement are provided in spacing. You provide the size and the spacing. So T12 at 200 amounts to 565.5 millimeter squared, which is slightly higher than 521. So you can go with T12 at 200 or you can even go with, maybe you go for 175, either way. So for the Eurocode, the formula is quite similar, it's almost the same thing. So m over bd square fck in this case instead of fcu, but fck is also fcu, so it also means the characteristic strength of the concrete. So that will give us our k, but k in this case, the limit for k is, instead of 0.156 in the BS code, it is 0.167, slightly higher in the Eurocode. So substituting our moment of 22.18, d of 124, fck of 20, so at the end of the day our k is quite similar to that of the BS code, but now it is 0.072 because of the slight reduction in the bending moment. So from here we can calculate our z, the same thing, but the formula for calculating z in the Eurocode is quite different from the one used for the BS code, but they are almost the same if you look at it. So to see that formula, you can check the Eurocode or you can take the course. So the AS, the formula for AS is, we reduce this factor of 0.95 in the BS code to 0.87. So it was reduced so that the moment will be, the reinforcement will be slightly higher. So at the end of the day, we have reinforcement of 538. You see, BS code is 521, Eurocode is 538. They are very close. So therefore, based on the design, you can provide the same thing, T12 at 200 spacing. But when we get to the end of this video, I'm going to show you something. But for now, let us have T12 at 125 for the BS code. You are going to understand the reason why I provided this T12 at 125 with an area of 904.8 millimeter square. Don't forget, the slab we are designing have a size of 5 meters by 5.5 meters. So if you are enjoying this video, you can like the video and even comment that you are enjoying it, so that other people can also get to watch the video. You can share it with your friends and your professional colleagues. So now that we've done design for the slab, like I mentioned, in slab you don't need to check for shear reinforcement. So the only thing we need to check for now is the serviceability of the slab, and this is where we have a huge difference between the BS code and the Eurocode. Based on the ultimate design, is quite similar. You can see that the area of reinforcement required is almost the same, then we can provide the same. But in terms of serviceability requirement, in terms of deflection checks, so you are going to see a huge difference between the two codes. So make sure you follow me and watch the video to the end. So now we want to look at the deflection check for the BS code and also deflection check for the Eurocode. So the first thing, we look at the BS code first. We need to establish in deflection check in the BS code, what was recommended was the limiting span. That is, the code tries to limit the span, the ratio of the span and the depth to a particular limit. So if this limit falls within the allowable, then deflection will be adequate. But if it falls outside the limit, then the deflection will fail. That is the idea in deflection check in the BS code. So if you look at the Eurocode, the same thing was also recommended, even though the Eurocode tried to buttress or try to provide other methods like calculation method. You can also find the calculation method in the BS code, but it is not really common like that compared to what we have in the Eurocode. So in a nutshell, in the two codes, the method of checking for deflection is the same. The basic span ratio. These are the two methods. The methods you find in the two codes. So according to the BS code, we first need to establish the actual span to depth ratio. What this means is the span of the slab to the depth of the slab. That will dictate the degree of deflection. So the actual span is 5 meters. Here we used to use the shorter span of the slab. You know, our slab we want to design is 5 meters by 5.5. So the shorter span is the one that we pick. So 5 meters divided by the effective depth 124. So if you do this computation, you end up with 40.3 as the actual ratio. So what the code is saying is whatever this actual ratio must always be less than the limiting for deflection to be okay. So if it is greater, you see that it will fail. It fails deflection. So now we need to know our basic ratio. Basic ratio according to the code is 26 because our slab is a continuous slab. What defines the basic ratio is the type of section, either it is rectangular section or flanged, and also the type of support, either it is simply supported, cantilevered, or continuous. Based on the layout that I show you, you can see that our slab is continuous in two sides. That is, it has slab in two of the four edges, so you can classify it as continuous. So because of that, the basic ratio is 26 according to table 3.9 of BS 8110. So because of that, the next thing we need to calculate is the stress ratio, and this one is given by this formula: combination of the comparing the required reinforcement against the provided reinforcement. Here, what we are going to do is we substitute 2 times Fy. We know what Fy is, the characteristic strength of concrete reinforcement 410. The AS required, that is the area of reinforcement calculated that was required based on calculation, divided by 3 times AS provided, the area of reinforcement you provide. Based on our calculation, the BS code has a area requirement of 521, while we provide, if you want to use T12 at 200, we provide 565. So if you substitute Fy, AS required, AS provided, then this beta is usually taken as 1. Substituting that, so you end up with 251.82 as your Fs. So the next thing you need to calculate after you get your Fs is the modification factor. You know, this is the basic ratio based on the code, but depending on the amount of reinforcement that you put inside the section, that can affect this ratio. So this ratio needs to be modified based on the amount of reinforcement. So that's why we calculate this. So in order to get the modification factor, we need to evaluate M over BD square. M is the moment, B is the width of the slab. We take it as 1 meter, as I've mentioned. D is the effective depth. So if you substitute that, you have 1.49. So the combination of Fs and M over BD squared will give you modification factor. This can actually be seen in table 3.10 of BS 8110, but I don't want to show us all that. So our modification factor in a nutshell is going to be 1.34 if you combine Fs and M over BD squared together. So but this modification factor must always be less than 2. Since this is less than 2, then we take it. Therefore, our maximum span ratio is now the basic ratio multiplied by the modification. So at the end of the day, if you multiply 26 by 1.34, you have 34.84 as the limit ratio. So you have to compare this to this. You see that at the end of the day, the actual is greater than the limiting. So therefore, deflection did what? Deflection fails. But if you look at it closely, you can see that the limiting is very close to the actual. Is very close. You understand what I mean now? But let us look at the Eurocode part. For the Eurocode, the calculation of the deflection is quite similar to this, but the formulas are very different. They are quite different. It's a different formula. So the first thing you need to know is your structure type. So this structure type, you can see it in table 7.4n of BS of the Eurocode 2. You find it there. So but based on this exercise, our type of slab K equals 1.3. So let's take K as 1.3. We have different types, either cantilever, just like the way we select this basic ratio is almost the same idea. So K is 1.3. So and then you need to calculate what we call the reinforcement ratio. So this reinforcement ratio is divided into three parts. You have the reference, this is the reference. Then we have the reinforcement ratio for the tension reinforcement. This is the formula, 100. For the reference, the formula is 10 to the power of minus 3 multiplied by the square root of FCK. FCK is 20. So if you substitute, you have 0.045 as our reference reinforcement ratio. Then the reinforcement ratio for the tension reinforcement. So the formula is 100 AS required at the tension zone divided by BD. So if you substitute AS required 538 divided by B is the width of the slab, times D, effective depth, you are going to have 0.43. Then we also have another parameter, which is rho prime. Rho prime is the reinforcement ratio for the compression reinforcement. You know, our section can either require tension reinforcement only or requires combination of the two. So but based on our design, you know, our K was less than the limiting, so therefore we only require tension reinforcement only. So therefore the rho prime, the reinforcement ratio for compression reinforcement is 0 because we did not provide any compression reinforcement. So once you're able to evaluate these four parameters, the next thing you need to do according to the Eurocode is now to calculate the, I will call this basic ratio, just like this, the basic ratio L over D. So this ratio is given by some formulas. We have two formulas in the code. I don't want to bore us with all of that. So those two formulas, they are divided into two depending on if rho naught and rho, which one is greater. So if rho naught is greater, there is a formula. If rho is greater than rho naught, there's another formula. So based on this, you can see that rho is greater than rho naught. So because of that, we use the second formula to calculate LZ. So what you just need to substitute is you substitute K and then you substitute rho naught and rho. That's what you need to substitute inside the formula. So but I don't want to show all those things so that this video will not be too long. So that's why we cut it. So if you want to see a full breakdown of where we have where in the Eurocode and the BS code, you can take the course. It's quite simple and straightforward. So now you can see a huge difference between the basic ratio in the BS code and the basic ratio in the Eurocode. So this is going to be a huge problem. So 14.4 compared to 26, you can see the difference. So the next thing is you now do what we called application of the reinforcement effect, just like the way we did in this step here, modifying the basic ratio. So but according to the Eurocode, there are three things you can use to modify this basic ratio. The first thing is the flanges. If you are designing a flange section, but you know it's a slab that we are designing, it is not a beam. So since it is a slab, there is no flange, so that factor tends to be taken as 1. The second factor is the effective length of the slab. So this is only applicable when the slab length is greater than 7 meters. But if the slab length is less than 7 meters, you don't need to apply that factor. So but because our slab length is 5 meters by 5.5, so it is not up to 7 meters, we cannot apply that factor. And then the third one is the reinforcement effect, which is this one, 500 divided by FCK times AS required over AS provided. You can see that it's quite similar to this equation, but because this is the Eurocode, so this is what we got. We got a modification factor of 1.32. So that means the limiting basic ratio according to the Eurocode is the basic ratio here, which is 14.4 multiplied by the modification factor. So you have 14.4 times 1.32. So you have 14.4. If you multiply it, you end up with 19.3. So you can see the difference. This is the limiting ratio according to the Eurocode, 19.3. This is the limiting ratio according to the BS code 34.8. So, and this is the actual ratio 40.5. So you can see that according to the BS code, if we can adjust the reinforcement required, then the section will pass deflection. But based on the Eurocode, it is too, the difference between the actual and the base and the limiting is too wide. So adjusting the reinforcement will not do anything. So it will tense it. The only thing you can do is to increase the thickness of the slab. With the BS code, if you provide T12 at 125, the slab will pass in deflection. But based on the Eurocode, if we use T12 at 125, the slab will never pass because the difference between these two is too wide. So the only thing you can do is to increase the thickness for the Eurocode, but for the BS code, you can adjust the reinforcement provided. Based on this design, you can see that the actual span is greater than the limiting in both codes. Therefore, the deflection will fail based on our provision of T12 at 200. But based on the numbers that we got, you can see that for the BS code, if you increase the area of reinforcement slightly more, the reinforcement will pass, the slab will pass. So you don't need to compare. Either you provide a slab of thickness of 150 and then area of reinforcement at a spacing of maybe 125, T12 at 125, or you go for thickness of 175 or 200 and a spacing of 200 and a spacing of T12 at 200. Which one do you think is more economical? So let me know in the comments, comparing the cost of concrete and also comparing the area of reinforcement that you need to provide. So I'm sure you've learned one or two things in this video. Now you see the design approach of the BS code and the Eurocode to slab design. I'm sure you liked the video. So if you want to learn more, this is our contact details, chefjinacademy.com. You can visit our website, chefjinacademy.com, to learn more on design. Or if you have any question, you can leave it in the comments of this video, or you can message me privately via this email, or you can chat me up on WhatsApp with this contact. So I'm sure you've subscribed to the channel. So before we end this section, I want to use this medium to inform you that we are having live session on this channel every month. That's going to be either the first Sunday of the month or the second Sunday of the month. So for this month, we are going to be looking at the cost analysis. In this video, we look at the design, the technical part. So in our next live section, which is going to be on Sunday of next week, so we want to look at the cost analysis of slab design, either to the BS code or to the Eurocode. So in that section, we go through the design just like this, and then we now look at the cost benefit. Which one will be more economical, either the Eurocode or the BS code? In order for you to join the live, you can subscribe to the channel so that whenever we drop the video, and then on the notification, so that whenever we start the live, YouTube is going to notify you. You'll be able to join the live and learn, and also ask questions directly from me. So thank you. I hope to see you then. See you in the next one.